Alright, so we just got done looking at a simulation to try to understand the idea we're going to talk about in this video. So what we're going to be talking about is what's called a sampling distribution. That's what our definition is here. So a sampling distribution allows us to model how a statistic, remember a statistic is a numerical summary of a sample, like p hat, and model how it behaves from sample to sample. So those pictures that we looked at in Stack Francis-Lee Applet, those were examples of what the model looks like. So we're going to talk a little about what this actually means and why do you care. And I already wrote this out so I could explain more than focusing on writing it at the same time. So our goal here is we generally take a sample to get some statistic like p hat to estimate the population's parameter like p. So what I mean, so thinking about like my big bucket of beads. It had black and yellow beads in it, and maybe I don't know what percent of them are black beads. So I'm going to take a sample, so maybe I'll pull out 50 beads, figure out what percentage of those 50 beads are black, and my goal was to estimate what the entire population, or what percent of all beads in there are black. That's generally my goal. Because I don't know a population parameter, so I'm going to take a sample to try to estimate it. So what a sampling distribution allows us to do is to model a statistic like p hat, and it allows us to know what types of values that we can expect to see. So what values are likely to happen versus unlikely to happen. So for example, if I actually found out that there was 40% black beads in my big bucket, there is probably not a very good chance that I'm going to get 100% black beads in my sample. I'm also probably not very likely to get 0% black beads in my sample. But I want to know what values are likely to happen versus what types of values are unlikely to happen. So now let's actually talk about what our sampling distribution looks like and what sort of model I'm able to use for it. So under certain conditions, which we will get to talk about shortly, we are able to say that p hat, which is our sample proportion, will be approximately distributed. Remember that big N stands for normal. And then the two different things that we need to know are the mean of my normal distribution and our standard deviation. So the mean is p, and our standard deviation is the square root of p times 1 minus p over n. Now, let's talk about what we did learn in our video last time. We learned, right, the mean and median didn't change based upon our sample size. So what you should notice here, n has no effect on the mean. We also learned that the standard deviation got smaller as our sample size got bigger. And we see that here as well, with n being in the denominator of our square root. As this number on the bottom gets bigger, this whole thing is going to get smaller. So we're seeing those ideas that mean was unaffected, and it sort of makes sense that if 40% of all of the beads are black, the thing I'm supposed to probably pull off most often is going to be 40% black beads as well. Standard deviation, not as obvious where the formula comes from. It's not real important to understand where it comes from, but what you want to understand is how the sample size does actually make the standard deviation smaller. So what would that look like in our example where we sampled 50 beads when 40% of all of the beads were black? So what that would mean for us is that p hat, which in this case is our sample proportion of black beads, will be approximately distributed normal with a mean of 40% and standard deviation. Well, I need to actually do my calculation. It's not as obvious to me here. So our standard deviation is the square root of p times 1 minus p over n. So in our case, this would be the square root of 0.40 times 1 minus 0.40 over 50, which turns out to be 0.0693. So that's my number that goes up there. Or so basically we're saying the mean is 40%, standard deviation is 6.93% once I change those two percentages. Now I mentioned that this is only under certain conditions that this is going to work. So we actually do need to talk about what those conditions are. So what are these conditions? So the first thing goes back to the beginning of our unit. We need a relatively random and unbiased sample. That's what my RRUS stands for. So relatively random and unbiased sample. So it goes back to the idea of making sure we're getting our sample selected in a good way. We don't have leading questions. We don't have a non-response bias that we need to worry about. We need to make sure that we're getting things in a good way. The second and third condition are basically a calculation that we're going to do. We need n times p to be at least 10 and n times 1 minus p to be at least 10. So really what this means, if we think about it in the context of our example, what n times p would represent is how many black beads I would expect to pull out. And the n times 1 minus p would be the expected number of other color beads, or in our case, yellow beads that we have. Basically, we need to have at least 10 black beads in our sample and at least 10 yellow beads expected in our sample. Does this work for my example? Well, I don't think I was doing anything intentional pulling out my beads. Like, I'm not going for a color or anything like that. So at least from what we know, that seems reasonable. Our n was 50. Our p was 0.4. So in a sample of 50 beads, I would expect 20 of them to be black, and that number is at least 10. In a sample of 50 beads, I would then expect that 30 of them were yellow, and those are at least 10. You'll notice that these two numbers here add up to your sample size. So it's how many you expect of for here as the one color versus the other color. And you'd have at least 10 of those. And once we know all this holds, then we can use our normal curve to apply everything else that we've already talked about with the normal distribution. So let's do this for our p of 0.4 and sample size of 50. So there's this calculation that we just did here. I'm going to use this mean of 0.4 and my standard deviation of 0.0693. Alright, so we're going to have our mean. Right, and then we go 3 standard deviations in either direction here. So my mean was 0.4. And then my standard deviation was at 0.0693, so I'm just going to subtract off 0.0693 to get this first value. And I get 0.3307. Subtract off 0.0693 again. And I get 0.2614. And subtract it off one more time going this direction. We get 0.1921. In the other direction, we're just going to add that 0.0693. So the first time I get 0.4693. The next time I get 0.5386. And then finally we get 0.6079. So now I can use that normal curve rule, that 68, 95, 99.7 rule. So what I know is that if I'm 1 standard deviation out, that's 68% of my data. So what that means for me. So when taking a sample of 50 beads, because that's how many we sampled here, 68% of the time we should get between 33.07% and 46.93% black beads. Because down here at the bottom, that's telling me my percent of beads that are black. So 68% of the time I should get between this 33.07% and 46.93%. Now if I go out that second standard deviation, that was when that 95% happened. So still when taking a sample of 50 beads, now 95% of the time we should get this time between 26.14% and 53.86%. Black beads. Okay. Then finally, if I go out that third standard deviation, this is where we should get the 99.7%. So then 99.7% of the time we should get between 19.21%, so that 0.1921 in decimal form, and 60.79% black beads. So now I know if I take a sample of 50 beads, what values are likely to happen, ones that are closer to the mean, which values are more unlikely to happen, ones that are further away. So right now, if you were to take a sample of those beads and tell me that you got 70% black beads, okay, that wasn't very likely to happen. I might think that you did something a little weird when you sampled your beads if you got 70% black beads. Because this allows us to know what to expect. So, what would change if he was still 0.4, but n was now 100? So how would this affect our sampling distribution? So first, how would it change our conditions? Well, it doesn't change how our sampling was done, so that's still okay. Now, n is different, so n times p is going to be a little bit different. So this time if I take a sample of 100 beads, I would expect 40 of them to be black, and that's at least 10. And then my n times 1 minus p, or how many yellow I would expect here, would be 60. Sorry, this 1 minus the 0.4 is just the 0.6 there, is also at least 10. So our conditions would still hold. p hat then will be approximately distributed normal. The mean is still 0.4. But remember, the standard deviation is our square root of p times 1 minus p over n. So the top is the same, but our n on the bottom is different, and we know sample size does affect standard deviation. So this one turns out to be 0.0490. So that's what's going to go in up here. And that's how it's going to change the sample distribution. So will it change my picture? Well, comparing it to before, it's going to, because this distance now is no longer 0.0693. This distance is now going to be 0.0490. So we're going to go ahead and draw that picture here and see what it looks like. So how does this affect our picture? Well, it does not change where we are centered at, because p is still our 0.4. But now my distance between them is a 0.049. So I'm going to subtract off the 0.049 and get 0.351. Subtract it off again, get 0.302, and subtracting it off again, I get 0.253. Now adding that 0.049 in the opposite direction here will get me 0.449. 0.498 and 0.547. So again, so I go out that one standard deviation, right, this is where we expect 68% to be. So then when taking a sample of 100 bees, so that is different than what we were doing before. 68% of the time, we should get between, this time our numbers are 35.1% and our 44.9% black beads. When I go out my second standard deviation, again we'll get 95%. So 95% of the time, we should get between 30.2% and 49.8% black beads. And then finally, when we go out our third standard deviation, is our 99.7%. So then 99.7% of the time, we should get between 25.3% and 54.7% black beads. So we would have a different expectation from a different sample size. So again, kind of comparing it, our numbers along the bottom are different. So different expectation. So what would then be the probability that if I took a sample of 100 beads, that a percentage of black beads would be greater than 30.2%? Okay, so things I know. I know I'm centered, still at 0.40. I did a sample of 100 beads. So all of my numbers are going to be the same along the bottom that I had here, because this is where we also had that sample of 100 up here. So I'm going to keep all of those numbers the same. Get those added here. And it asks us for greater than 30.2%. So I know I want everything greater, which would be everything to the right. Okay, so let's break this into things that I do know. I know that if I'm 2 standard deviations out, and the reason why I'm saying that is because the 30.2% is 2 standard deviations below, that I know that this piece here, that's 95%. Right, I know that from what I was just looking at, so 95% is between there and there. Now what I have, so I have this big piece labeled, and I have these 2 other pieces that aren't labeled. Well, my entire picture adds up to 100%, and I already have 95% there. So I can only add 5% more to my picture. I have 2 different spots to put it in, so I'm going to split it up. And so this little piece is going to be 2.5%, and this piece is also going to be 2.5%. So what's going to be my total percentage that's between there? Well, it's going to be the 95%, this piece, plus the 2.5% piece over here that I have shaded. So that is 97.5%. Okay, now one thing we do is we interpret these a little bit. So what this means is, so if 40% of the beads are black, or that was an assumption I made, that's kind of the bucket I was drawing from. When we take a sample of 100 beads, that was our sample size that we had here, we should find at least 30.2% of them to be black, about 97.5% of the time. So 97.5% of the time you should get at least 30-ish% black beads. Only 2.5% of the time would you get anything lower. So just using that 68, 95, 99.7 rule to help us find that probability. What if instead I wanted to find the probability that the percentage of black beads is greater than 33%? I'm going to start with my same picture because I haven't changed the beads I'm working with, I haven't changed my sample size, so I'm going to have all of those same numbers along the bottom here. not changing any of that. So now it's asking for greater than 33%. Well, 33% is somewhere over here. Right, because 33% is 0.33. And I know it's everything greater. And I know that's what my picture looks like. But our problem here, I can't use what I know. Here's the things I can find out. Right, if I go one standard deviation out, right, like I know this piece is 68%. I can also then find actually that this piece here is 16% because that half of 32%, that leftover piece, is there. But how big is that piece? I don't know, right? Because this 0.33 is not one of our numbers along the bottom, or not one of the marks. So that's making it harder. But what I do know is I have had something like this happen to me before, back in Unit 1. And so I know I can actually find this probability. We're just going to have to think through how I can do it. And that's what we'll pick up in the next video.